Welcome. After last week's stream I had with Danis and Adrian, I figured I want to sort of condense the whole topic of cohesion down into a shorter video. So I want to go over a few of the metrics that we've also discussed. What is cohesion to begin with? And then I will look how to use these metrics and what tools specifically NDepend offers to analyze cohesion problems once you detected it. So we go over definition, usage and detection, and analysis. Now let's first look at the definition of cohesion, simply by just looking at Wikipedia. What does it say? Cohesion refers to the degree to which the elements inside a module belong together. Well, first of all, that's a discussion we had last week as well, which was interesting. Like, how would it translate to non-object-oriented languages? Technically, just consider modules, or we had this discussion where React components could be considered modules. But it's about as it says here as well, it's a measure of the strength of a relationship between the methods or the behavior and the data of a class or a module. So it's like, this is can be confusing. So I think a picture says more than 1,000 words. Let's just look at the simple picture, which takes into account coupling, and this shows you essentially why coupling and cohesion are often mentioned together. Because what you're seeing in the blocks in the cubes is essentially a cohesive module, which is one entry point. Now, it's not necessarily that a module has one entry point, but there's a single graph, so it relates to all the data in the module, which does not say what a dot exactly represents. It could very well be that these two are still methods and these three dots are actually the data. I mean, that's a bit like not necessary for the visualization. And here you see exactly the same. Or you could say, okay, maybe these are methods, and these are also private fields. You see a certain amount of coupling within this module, then, for instance, which you can discuss about in terms of, is that what you want? Because this could indicate that you need to do, let's assume that this is a method and this is a method. That would then imply that, for instance, you might need to first call this method before you actually access the variables yourself or whatever. So, but that's a different discussion that goes beyond sort of visualizing what cohesion means or the lack thereof. This is essentially high coupling and very low cohesion, because like the responsibilities are probably fragmented or something. But I think this speaks a lot to what it actually means visually when they talk about cohesion and coupling, because you have low coupling here. You have just one entry point / exit point between these two modules. So this is a good visual representation of high cohesion and low cohesion. Now, what's interesting about this article is that it actually defines different types of cohesion, from worst to best, and certain types of cohesion are basically not possible to prevent and others are. Let's briefly go over them. So coincidental cohesion is just basically arbitrary grouping of methods and code. And what I think is interesting about the logical cohesion is that it says when parts of a module are grouped because they are logically categorized to do the same thing, even though they're different by nature, e.g., grouping all mouse keyboard input handling routines, or bundling all models, views, and controllers in separate folders in an MVC pattern. Now, this is interesting because this is cohesion in the context of a namespace, for instance, and not necessarily a class. So there we have a different kind of module. But so this is an indicator that cohesion is a concept that basically repeats in the layers of your code, especially if you look at it from this perspective. And I think visualizations that I will show later will also show that. But more about that later. Now, temporal cohesion is when you group elements together because they relate. There's a time relationship between the two. Um, there's sort of a relation between coupling and cohesion here, is that they use similar terms. If you look at Kinesence, they have similarities in their definition. So it's not always that easy to disambiguate these concepts, because high cohesion in a or class essentially means that the elements of those class are highly coupled. So it basically depends on the context. You could use both terms interchangeably. That could make it confusing, especially because here they're now also talking of a bigger context, which could be a namespace of multiple classes. So yeah, I just wanted to make clear sort of that it's not necessarily something that you also always look at just from a class perspective. It's a sort of a recursive or fractal pattern that repeats itself over layers, and so it translates to different layers in your code essentially. Well, that was the temporal cohesion. Procedural, so it's not necessarily in time, but there is similarity in terms of that. Those elements are called in a specific sequence, which implies that you need to call one before the other. So there is a sort of a bit relation to the temporal one, and then the communication or informational cohesion, because they operate on the same data. Well, that sounds like sort of the definition of cohesion that we were talking about. Hence, this is not necessarily bad. While the more you move up, and it's a similar way as Kinesence speaks about coupling, the worse it is. Sequential cohesion is when parts are grouped together because the output from one part is an input for another part. Which is weird, because if you would make that too, like the then you get like a pipeline where the individual nodes or processes in the pipeline are cohesive, but you could assemble them in different ways. So what does it say here? E.g., a function that reads data from a file and processes the data. These, you could say this is two different classes. So this is, I would sound a bit more like coupling. So I don't really find this a very strong definition, because it can be confusing. Are we still talking about cohesion here, or are we talking about coupling? Because those elements in that assembly line, those should be the cohesive units. You could say in the context of a bigger, the next layer, then it makes sense to put them together because they're always used in this sequence. So you group the elements of a pipeline together. Could do it, not necessarily. Functional cohesion, that's basically saying, okay, this is the kind of cohesion you were expecting, as in these are arithmetic operations. It's not that strong in terms that there is no, these are basically pure functions. So it's not really module data that's being operated on. So I also think this is not necessarily a very strong example to explain cohesion in the context of what they're explaining here, that it's the degree to which elements belong together, i.e. the methods and the data, because there is no data in this example. The only data is the input. perfect cohesion is atomic. I think what's interesting is what they explain here. Uh, that they're not referencing here to perfect cohesion. If you go too far with cohesion, you basically get just a set of single functions that it's has a lot there's a lot of coupling in between, and it becomes very hard to understand the code. So you have to find a certain balance there. Hence, how do you uh, assess the metrics? Let's first look at the metrics now. Now, there's four, like the main metric, of which you have four totally different definitions. It's lack of cohesion of methods. That's what it's called. It's also called LCOM. Now, I've looked up, I found a good article in this Wikipedia article that explains all three of them. And basically, it says, well, LCOM 1, which was the first one, had a lot of drawbacks in terms of, and it's explaining it here, I think. Uh, yeah, well, basically, there were issues with false positives or maybe even false negatives, that the usability of the outcome was hard. For instance, when you had getters and setters, it was not performing that well. So if there's a lot of noise in the metric, it becomes hard to actually use it in the production, because then you do still need to do a lot of manual filtering. So then there were outcome 2 and 3, which are the ones which are used by NDepend. They have the same formula here. See, outcome 1 is 1 minus sum of the method fields divided by the methods times the fields, which is this one. It's just different definition, but it's exactly the same. So I wasn't aware of sort of this 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 is a good disambiguation of, okay, which one is which, because NDepend apparently uses outcome 2 and outcome 3, but the outcome 3 definition is what they call Henderson and Sellers. So this ordering is also confusing here. So let's just, because they don't really clearly say which one is now Henderson, Sellers, or Constantine and Graham, but let's just assume the NDepend definition here is right, that this one is regular, was what they call LCOM, which is then LCOM 2, and LCOM 3 is an iteration on that, or an evaluation, evolution, and that's LCOM 3. Now, LCOM 2 is the percentage of the methods that do not access specific attribute averaged over all attributes in the class. So it's basically counting and then averaging, and outcome 3 works in a slightly different way. But I think if you look at outcome 4, the main definition is that outcome 4 really works on the graph, while outcome 2 and 3 are basically derived attributes from the graph of a class. Let's just stick to class for now for the explanation. So where outcome 2 is between 0, which is like totally cohesive, and 1 incohesive, i.e. lack of cohesion of methods. Outcome 3 is between 0 and 2, where 1 is no cohesion, and then everything above 1 is basically problematic. Now, there's outcome 4, which is the recommended method, but I have some questions about this. But basically, the simple explanation is that it counts the distinct graphs in a class. Now, if I look at a tool which is using outcome 4 and compare it to the graphs, I have some unclarities about the implementation. So let's start from there, and then we'll go back to outcome 2 and 3 and how they are used. So a tool that is using Alchem 4 is Cohesion. And I know that because I've done this code base more often. There's two classes that are also hotspots, i.e., are touched very often, that have cohesion problems. Um, and if we open this one, the abstract entity persister, and we review it, then it says, okay, it has low cohesion. It actually says it has. This is the wrong one. Let's just do it. I want the abstract entity persister. It says it has 10 different responsibilities. So it has a clear number. So this is definitely this is probably the result of Alchem 4. So it counts 10 distinct graphs. Now, and there's another one, and then I'll show you the graphs, the actual graphs in NDepend, which is the join walker, where it says it has 3 different responsibilities. So if we look at the graphs of these classes, we would expect like separate graphs. Now, let's then take a look in, because that's where NDepend is good at, visualizing these graphs. So if we look at the join walker, we can say, okay, I'd like to see this on the dependency graph. Here you can clearly see, let's unselect this. Well, I can clearly see, I don't know how clear you can see it, but here you see like at least a separation of 2 graphs. So basically this is one, and I'm not sure if this is also one. No, because you do see that this is interconnected. So this goes all the way up here, which is also connected to that. So I am only seeing, when I look at this, I am seeing these are like 2 distinct graphs for sure. So I only sort of looking at it, glancing over it quickly, I am not capable to find 3. So I'm not 100% sure how, first of all, how the calculation in Cohesion exactly works. But if I now go to the abstract entity persister, which has 10, then I would expect to see some. What is this? Let's try. This is not what I am expecting. NDepend. I think I'm just showing a method now. Oh, I'm in the wrong file. I'm in the wrong context, I think. There's an inner clause. Here, this takes a bit longer. Well, shoot me. These are, I think, protected methods that are used by subclasses. I find it hard to actually say, okay, there's, from how you see the algorithm rendered, I think I would expect it to be easier to find distinct graphs here. Maybe they're very small. Maybe this is maybe one. This could be one. Anyway, I don't think if I can get to 10, because here you see actually that there is a relationship which then ties into the lockers, which then also have other dependencies. So it doesn't really visualize distinct graphs. So that does not necessarily make the metric less valuable. I'm just showing you the difference, how the outcome translates to a visualization. So Alchem 4 is used by Cohesion, which logically it says, okay, you can extract a class, which is a good refactoring. I want to go into that and just do some experiments using the tooling that I'm showing you right now, also in NDepend, how to refactor this. So this is for Alchem 4, which definitely is capable of identifying some problems. My initial expectation was that it would not work on a class, but apparently I don't exactly know how it's implemented. So I should actually replicate it myself to really understand it. But now we come to the point how to use them. Basically, what we saw in the definition, everything above one you should take into consideration, because then there's two distinct responsibilities, two distinct graphs. You should be able to split that up fairly easily. But that does not mean that you get a more cohesive class if you look at the abstract entity persister, because there's still a lot of entanglement. So I don't know how it gets to 10. Let's put it that way. But that sounds about right. For the other two metrics, the recommendation, so let's just follow the recommendation of NDepend. It is it's everything above 0.8 is a potential issue, but you have to take into account the number of fields in terms of if there's more fields or methods, then there's the likelihood of it being an issue is higher. So we could validate that in NDepend, because we're basically, what I really like about it, we could write a query. Let's just do that. Let's close the graph for now. It's probably sucking up resources. No, I don't want that. I think I already wrote it. So basically you can use a language. Maybe there's also a number of methods. So if we order by lack of cohesion of methods, and we just go over these, it's basically would say, okay, this is probably not an issue. So look at if we just open up the code, or if, see, it's not a big class. So that's their way of filtering out potential false positives. So if you want to assess the values, you should actually do a sort of derivative query or alarm that triggers on it. I don't know. They actually use it in their own query for let's see, object-oriented design. I think it. I'm not sure. I do know that they have it somewhere. I don't see anything with cohesion here. Architecture. Code smells. Oh, poor cohesion. Yeah. So they actually also implement that in their own rules. See, and they actually even increased the threshold to 0.91. So it identifies that one, but it does not identify the join walker, because I don't know. Oh, it's ordered invert. I should filter out maybe. Let's just take their own recommendation and order it, so we don't have this huge list to go over. Still a lot. Join Walker, here it is. 0.93. And that's interesting. I'm not sure why it's actually not showing up here. Don't they do a count of properties and event access? They do a bit more processing. I actually look into this query first time. So there's a lot more going on here to filter out results. Here you see that that they implemented more logic to assess it in their usage, which is based on experience. So in that respect, that's how you can use the outcome. And they're also having the Henderson sellers. What I found interesting there, if you now this is a bit more scrolling, that here you can see that I noticed that when the delta between these two is high, that's probably a false positive of lack of cohesion of methods. Not this one, but I don't know what this is. This is like small sealed glass. I'm sort of surprised, but that's probably, it has a variable which is not accessed by these functions. So that's why this one has a very high outcome, like this is outcome 2, but not a high Henderson sellers. So using that in conjunction, but it would also be filtered out because it doesn't have that many fields. But it does indicate, it's an interesting question why it's built like this. So design decision wise, it's storing some state in probably some iterator or something. So yeah, I found that interesting to look at it from a different perspective and how you could use them in conjunction. On the other hand, if we say, let's just look everything, is everything only above 1 justified? Let's just put this filter back on. Because here you have a Henderson sellers of 1. Which doesn't really look that alarming to me. So you see that they both have their false positives, which may be why the outcome 4 is more appropriate here. I mean, I can just open one in a dependency graph. You see that it's much more, it looks like a neat, small, cohesive class. So presumably the outcome 4 has less false positives, but I can't put the results next to the results of NDepend. But that's how you could use these. Cohesion does a lot for you. NDepend implemented some heuristics in the queries themselves to filter out more false positives. So here, I think this is a nice example where you can actually see them perform and see where they deliver false positives. I don't know about the false negatives, which would be worse, but I think classes that have low cohesion would probably show up in other metrics as well. So here you see like metrics are indicators, but it really helps if you look at the data in conjunction with other data, as Cohesion is doing, which is also taking along the time dimension. Now, one more thing I wanted to show you is inspecting incohesive code. I already showed you the graph where for certain cases it can really quickly help you identify easily separable issues, because Cohesion tells you, okay, yeah, there's more responsibilities, but which graphs are separate, it doesn't really tell you. I think let's just look at whether it does in the Cohesion in the X-ray, because the X-ray is actually going a bit more in depth. So maybe while that's running, my mouse is not working this well on this table. Let's look at the join walker from a different perspective. Join walker. So come again. Here's the graph. Now there's another tool in NDepend which I showed last week. which is called the DSM, or the dependency structure matrix. Now, let's open this file in the DSM. And if we say, okay, I want those to be equal, and I also, the DSM is basically another representation of a graph. So each cell in the DSM is basically representing a potential edge between the nodes which are in the columns and the rows. Where is it? So you could inspect whole namespaces on this and see their relation. Oh, I do want to bind them. Or you could do it for a single class. Now, what I'm doing here, so where you see the colors, it's direct and indirect dependencies. And you start to see a few blocks appear. So this is interesting because this is maybe clearly showing the three different graphs. Because as you can see here, there's relationships between the nodes in the rows and columns that don't have any other hits. So I think an easier way to just visualize it is just only showing one direction of the dependencies, because it becomes a bit easier to reason about, because that basically implies, if I hover over, that the column here has a dependency on the row, and the other way around is basically how much colors are there. So I think this makes it easy to reason about, but you miss the clear squares. But here you see that there's two methods that are acting on a set of other fields or methods which are not being accessed anywhere else. Here you see exactly the same, and here you see also a very distinct set of responsibilities. And then there's like some other, this is probably a constructor. What is it? So, but there is methods which are acting on variables that are also being used in other columns. So this for instance might be a variable you want to share. So often what you'd see is that what's lower in the DSM are the fields or methods that are used by a lot of other fields or methods. And if you see like very blue columns, it indicates that one method is accessing a lot of fields, which often, for instance, could be a constructor. Now, what's interesting is that this pattern, if you can also see that on a namespace level. So this is because this explains a bit better what cohesion looks like when you do it on a namespace level, and also how it then. So let's just open this one. I just want one. Let's just do a simple one. I know that this is a small namespace with not that many classes. So it becomes a bit easier. Now let's say I would open up all these classes. Let me turn on display all. So what the triangulation function is doing, it's actually here visualizing a proper layering, which you can see in the graph. Mouse is tripping balls right now. Here you see that there's a like a lower level class that's being used by classes up higher. So I should need to close the classes again. Let me see, because I can hardly read it myself. So here you see the configuration XML helper, which is, and this is predominantly this method maybe that is being used by other classes. So often you see a pattern where the base values of whether it's a namespace with multiple classes or a class itself, you can distinguish the responsibilities there as well. If we do maybe just direct members, the squares become a bit better visible, a bit better. Here you see a similar thing where you see squares emerge of the cohesive parts, which are in this case just the classes. So they interact predominantly with themselves, and there's some interactions with other classes. So the dependency matrix can help you identify the zones of responsibilities much better than sometimes a graph can, as I showed you for the join walker. And now let's just do the abstract entity persister as well. Let's see if we put this one. Now this is going to be huge, so it's hard to read on the screen probably. But what you'll see here, and let's just do it with all the members, direct and indirect. Here you start seeing clusters to appear as well. And as you can see, they often also, so there is a set of fields that is used by many different other methods. So if you translate that to classes, this would be the class that's in the bottom of the graph, or depending on how you're ordering, but that's the lower layer. And there's sets of responsibilities that, although they use other parts, they also have a clear cohesive structure here and here, for instance, which you can extract into another class, for instance. So this is what I wanted to show you. I've showed it in multiple streams, what you can use to actually distinguish cohesive parts and very incohesive classes, and that can give you a very good indicator where the seams are and where you can make extractions. So well, this is what I wanted to show you, a bit more condensed form of the explanation about cohesion, how you can find it, which different metrics there are, what's the differences between them, how you should interpret the results, and also what tools are there, visualizations that can help you deal with them. So identifying them is one, but then fixing the problem is another one. I'd love to go into that and do an experiment on that later, but I believe this already gave a great indicator of how you can use the DSM and the graphs to refactor your incohesive classes. Well, thanks for watching. See you in the next one, because I want to do a similar video on coupling. Goodbye.